Hello everybody and welcome to another contemporary math video. This is for section 4B, as you can see here. And we are going to cover exponents in this video, some exponent laws, roots and radicals in this video, and we will be just doing a quick review of easy equation solving as well toward the end. So let's hop in. When we look at these particular examples here at the top, these get to exactly what exponents are and how they work. So we call the big number here the base, and we call the smaller number up here, that is what we say superscripted. We would call this the exponent or the power. So this would be 5, you could say 5 to the second power. And all that's telling you to do is to multiply two factors of 5. Boom, boom, 5 times 5. Similarly here, this would be 5 to the third power. So we would be multiplying 3 factors of 5. 1, 2, 3. And very similar case over here. So you know in this course, at least, we've discussed how to multiply powers of 10. So when you multiply powers of 10 and they have the same base, they're both 10, we can just add the exponents together. If you divide powers of 10, again, they have the same base, we can subtract the exponents, top minus bottom. If we raise a base with a power to another power, we can multiply those powers together. But everything works exactly the same, even if we have a base that is not 10, as you can see in these three examples on the other side. So here we will have, one second please, here we will have 7 to the 7th power because we can add the 4 and the 3 to get the 7. Here we will have 3 to the 4th power because I can subtract the top exponent minus the bottom. 8 minus 4 is 4. And here in the last example we will have 2 to the 6th power because I can multiply these two exponents together. I'm going to sort of jump the screen up here a little bit. This zero power rule is what we're going to go over next, but I'm going to pause it and move it up in a jump. So here we go. Okay, so zero power rule. You can see here we have this sentence, any base raised to the 0 power is 1. So what that would look like, it would be m to the 0 power equals 1. Now there is one little caveat, m cannot be 0. And if you want to know more about that, you can get a hold of me personally. So m cannot be 0, but why? This rule is just very strange looking. If you raise it to the 0 power, shouldn't it be 0? How is it 1? Well, that's what this explanation is right here. So I'm going to try to do a better job to attempt this. We know that if you have x cubed over x cubed, that anything divided by itself will cancel out to be 1. Now, if you think of this a different way, I'm going to use a different color. If you have x cubed divided by x cubed, and you do what we did above with the subtraction, this would be x to the 3 minus 3. Well, that exponent becomes 0. So what we did was we started with x cubed in both of these scenarios, the red scenario and the blue scenario. And we did one method and got 1, and we used another method and got x to the 0. So since we started at the same place and didn't break any math rules, we get to say then that 1 is equal to x to the 0 power, which is what was trying to be said over here on the left side of this page, but it was a little broken out a little bit funny. So this example over here with words, I think, will make a lot more sense. All right, negative powers. Now I want to back this first example up a little bit, so hopefully it'll make more sense. I'm going to write 5 to the 5th power over 5 to the 7th power. Now, I just got done saying a few seconds ago that we want to do top minus bottom. So 5 minus 7 is in fact negative 2, right? So this fraction would leave to 5 to the 5 minus 7 power. 5 minus 7 would be negative 2 in the exponent. However, in math, we don't like having negative exponents. So what we do then is we take the base and the exponent and we can swap it to the other side of the fraction, being over 1. We can swap it to the other side of the fraction from the top to the bottom. And what that does for us is it gets rid of the negative exponent. From there, we can apply the square, the exponent, to the base. 2 factors of 5 multiply to 25. So for this example over here, we can do something similar. We can say, hey, this is always, you can always put anything over 1. What this negative will do is it will tell us to put this into the bottom of this fraction. And what's going to happen is the 1 will go up and the 2/3 will come down. Well, 2 times 2 times 2 in the denominator would become 8. And it works if you have a negative exponent in the denominator as well. So if you had 1 over 3 to the negative 4th, this negative tells you you will put the 3 to the 4th power in the top, and it is now over 1. You don't have to write that though, but that would be 81. All right, next, inverse operations of powers, which we will call roots. So most people are familiar with square roots, so you can square root perfect square numbers, and yeah, we'll most likely be using perfect square numbers here. So we will also be doing what we say cube root, so you can say third root or cube root here. Here you can say square root, or you can say second root. Here, and I keep putting these numbers here like second root, third root, because after you get to 4, we don't say the quartic root or anything like that. We just say the 4th root. So you can always use the numbers. This is the 4th root. But if you use a calculator, you can get that this will be 3 and 2. Or we can interpret these roots as rational or fractional powers. Now, this notation is a little off. I would write it like this, horizontal fraction. That way you knew it was going to be half power. But what happens here is whatever number is in the root will go into the denominator of the exponent. So this is equivalent to the square root of 25. And the square root of 25 is still 5. So what you want to do is you want to rewrite these to have them make more sense. We did this one right up here. That answer is 3. But you'll notice that the denominator is what's going into the value of the root here. We did this one right here, and that answer was 2. So just being able to convert into radical notation or root notation is very important. So with these first 8 examples, go ahead, pause the video, see if you can get answers to these. I will come back with full solutions and explain each one step by step. So hopefully you got these answers. If not, no big deal. I'm about to go over it. We have here 4 to the 3rd power. The 3 means we will have 3 factors of 4. So 4 times 4 times 4 is 64. 3 to the 4th power means we will have 4 factors of 3, so 3 times 3 times 3 times 3 times 3 is 81. Now example 3 is a little bit odd. This is e to the 7th power, and e is approximately 2.71. But for this particular example here, you will want to use a calculator. And on a calculator, you'll see something maybe like e with a little box up here, or e with a caret up here, something like this. And then you'll just type 7 after you find that button. But the exact answer is e to the 7th power. The decimal approximation, which is going to make more sense to most people in the real world, is 1096.63. And again, just be wary of how many decimal places you're supposed to approximate to. I just went out to 2 places here. So here we have 5 to the 6th power divided by 5 to the 2nd power. So I set it up as a fraction so it would make more sense. 6 minus 2 is 4. So we would have 4 factors of 5, which multiply to 625. With this next one, we have a base raised to the 0 power, 1. Pretty straightforward. With this next one and the last example here, we have negative exponents. So with example 6, we have 7 to the negative 2 exponent, or 7 to the power of negative 2. We want to get rid of that negative first. So what we do is we put it into the opposite side of the fraction, and then we get to eliminate, that's how we eliminate the negative that was in front of that 2. So we have 1 over 7 squared. 7 squared is 49. It's in the bottom here. It stays in the bottom here. So 1 over 49 is your answer. Next, we have 9 to the 1/2 power. And I know that looks a little bit clunky. 1/2 power. That's what this means. It'll be much more clear when you're working through your assignments and on exams. But half power, anytime you have a fractional exponent, you want to rewrite it in root or radical form. So 1/2 just means we are taking the square root of 9. And the square root of 9 is 3. No problem. The last example here, example 8, 512 raised to the negative 1/3 power. You want to get rid of that negative first. So the negative, again, pushes it down into the other side of the fraction. So we will have 1 over 512 to the 1/3 power. Then we can take care of the fractional exponent. 3, the denominator, is what goes into the root. So this is 1 over the cube root, or the 3rd root of 512. And the 3rd root of 512 is 8. So moving on, we have just a very, very short lesson on solving equations. You're more than welcome to watch any of these videos here. Any of these links up here that are still active, I will put into the description so you can watch them. But we're going to move on with solving these little equations down here. So how this works, you want to get the variable by itself, aka isolate the variable. And the variable is just the letter that's in it. Normally the variable will be x, but sometimes it can change to different letters, as you can see, p or t. And you just have to keep 2 very important rules in mind. You have to use opposite operations to isolate x, and what you do to one side, you do to the other. That way we can keep the equation balanced. So here, I have an x on the left side of this equation, for example 9, and a 9 is being subtracted from this. If I wanted to isolate this x, I would have to use the opposite operation to get rid of that 9. And I have to do it to both sides. So what happens here is -9 plus 9, anytime you add or subtract in an opposite fashion, that'll always end up being 0. So they reduce away to 0. Most students have heard and like to say they cancel to 0. So on the left side of the equation, we're just left with x, and on the right side of the equation, if we just add 3 and 9, we will get 12. We've isolated the variable x equals 12. For the next example, I have 4p equals 20. So with this, 4 is being multiplied to p. It's not notated there. So if you see a number immediately next to a letter, this implies multiplication. And the opposite of multiplying is dividing. So in order to get rid of this 4 that's being multiplied to the p, we would have to divide by 4. But we have to do it to the other side as well. That way, we keep the equation balanced. Now, on the left side, the 4 divided by itself, anytime you divide or multiply to get rid of a number, it will reduce to 1, as you can see right there. So we have a p on the left side, and on the right side, we have 20 divided by 4 is 5. And we've isolated the variable. There are no other numbers on the left side with p, so we're done. So with this next one, number 11, we have to put a little more thought into it. We have to get all constants on one side first. So what that means, a constant means there are no variables attached to that number. So I'm looking here at 2 and 17. I need to have 2 and 17 be on the same side of the equation. And in fact, they need to be on the opposite side of the equation from the variable. So I already see 17 is on the opposite side of the equation from the variable. That means we need to get rid of this -2. So I'm going to add 2 to both sides. That's how I'm going to cancel out the -2. And I will get 3x equals 17 and 2 is 19. Well, now this looks like the equation we did right over here. A number times a variable, yep, equals some other number, yep. And you know how to solve that. We can just divide by 3 here. That will cancel to 1 or reduce to 1. And I get x equals 19 over 3. Now, here is something that is super important. If you have a fraction for an answer, like 19 over 3, you have to check to see if it reduces. Luckily, or I guess luckily for everybody out there, this fraction does not reduce. So we can say that x would be equal to 19 over 3. For these last two, number 12 follows a pretty similar scenario to number 11. We have to get all of the constants on the opposite side of the variable. So here we go. That just means I'm going to subtract 4 to zero that out, and I will have t divided by 3 equals 6. Now this one's a little bit different because I said it already, t divided by 3. Most people say t over 3, and that's fine too, as long as you understand that the over means division is happening. So to get rid of a division, I'm going to multiply by 3. And when you multiply by 3, these 3's will cancel or reduce into a big fat sideways 1. So that leaves me with t equals 3 times 6 is 18. Now the last example here, we have variables on both sides of the equation. And I don't like that. I want to get all of my variables on one side of the equation. Most of the time we push all of the variables to the left side of the equation. There are better ways to do that, or different ways to solve this, but this is how I will do it. So I'm going to subtract 3x from both sides, and I can combine these x's with these x's. So over here we're doing some addition or subtraction, so that means this will zero out. We will have 2x minus 1 equals 7. And now this equation here looks a lot like this equation that we started with here. Pause the video, see if you can solve this one the rest of the way. So here's the rest of the solution. Again, we need to get all of the constants on the opposite side of the equation, so I will add 1 to zero these out. And then I will divide by 2 to reduce the 2's and get x equals 4. I hope this helps you guys. Good luck.